In this class, we continue the discussion on problem formulation. We look at the formulation and solution of the bin packing problem. In the previous classes, we have solved other examples that we have seen at the formulation stage of this course. So, we look at the bin packing problem, briefly look at the formulation and then explain how we solve this. If you would remember, this is a formulation where we defined binary variables or 0, 1 variables. The bin packing problem is as follows. You are given 8 numbers in this example. These 8 numbers are the number 8, 6, 9, 28, 17, 24, 7 and 21. Make minimum number of groups such that the sum of the numbers in each group does not exceed 45. Now, this is like saying these 8 numbers are like 8 items which have to be packed in a one dimensional bin of length 45, and we want to use minimum number of bins, and that is how this problem gets its name of one dimensional bin packing problem. We started by giving a simple solution and said that a simple solution would have, the solution given here has 4 groups. The lengths 8, 6 and 9 can go to one group, 28 and 17 can go to one group, 24 and 7 can go to one group, 21 is a group by itself. So, this simple solution has 4 bins. Now, the moment we have a simple solution with 4 bins, the question that we have is, can we solve this with 3 bins? We also mentioned that a formulation for this problem would have 36 variables and 12 constraints and simpler than the previous formulation, because an earlier formulation we could start the bin packing problem by saying that we can think of maximum of 8 groups because there are 8 elements, and we would like to minimize the number of groups into which these 8 elements can be packed. So, if we use 8 possible groups and 8 possible bins, the objective will be to minimize y1 up to y8. Each number should belong to only one group. So, sigma xij summed over j is equal to 1. So, x11 is 1 if the first number or the first item is allotted to the first group, x21 is equal to 1 if the second item is allotted to the first group, and so on. So, all those items that are allotted to the first group, the total should be less than or equal to 45. So, the constraint will have a right hand side of less than equal to 45 y1. y1 is equal to 1 if bin 1 is chosen or group 1 is chosen. So, whatever is allotted to that group should have a length less than or equal to 45. So, a general form is aa xij less than or equal to b into yj, where b is the bin capacity. Both xij and yj are binary variables, 0, 1 variables. So, if we start with 8 possible groups and then try to reduce it, there will be 64 xij variables and 8 yj variables. We can try and reduce it a little bit by looking at the simple solution with 4 groups. Therefore, if we have a solution with 4 groups, then we could think of 8 into 4 32 xij variables and 4 yj variables. Now, we will formulate this problem to see whether a solution with 3 groups is possible. The formulation with 4 groups would have 8 into 4 xij 32 xij variables and 4 yj variables. So, it will have 36 variables and 12 constraints. So, let us show this formulation on the Excel sheet and then show the solution to the problem. So, this is the formulation. I have shown x11 to x81, 14 to x84 here, indicating that these are variables that represent item going to bin. So, x84 represents item 8 going to bin number 4. y1 to y4 are the 4 bins that we have, because we are right now looking at a solution with 4 bins. Now as we did before, we give values to the x variables and y variables. So at the moment there are some fractional values, so all these have to be integers. So I am just giving them binary values. So I am just giving them 0 and 1 and those kind of values. So this is a solution that I have indicated. It may be feasible, it may not be feasible. Now we will check whether it is feasible or not feasible. At the moment it is not feasible, because I have put item 6 to 2 bins, which is not feasible. So I change this, I change this. So now we observe that here is a solution where 4 bins are there. The first bin is having items, this item and the third item. The second bin is having this third item, item number 5 and item number 8. The third bin is having item number 6 and the fourth bin is having item number 4. Therefore there are 4 bins, which is given in this solution. Now there are the constraints. So for every bin, the length of the items allotted to that bin should be less than or equal to 45, and if that bin is chosen. So let me just show the first left hand side of the first constraint. So this we will realize that it is 8 into B7 plus 6 into C7 and so on, minus 45 into B11. So let me explain this. So B7, C7, D7, E7, F, G, H up to I7 represent the values whether this item is going to the first bin or not. So in the feasible solution I have given this item is going to the first bin, this item is going to the first bin, this item is going to the first bin. So some of these 3 lengths we need to check. The 3 lengths are 8 for this one, 6 for this one from C7, and H7 is 7. So 8 plus 6, 14 plus 7 is 21 is less than 45. So you have a minus 24 here, because I have put minus 45, B11 minus 45, this bin is chosen. So this bin is chosen. So 45, it can give us a capacity of 45, 21 has been put. So the balance 24 is showing as minus 24. Similarly, for the, if we take the second bin, we realize that items number, this item and this item are in this bin. So this item, so let us look at this. So this item has a length of, this is D8. So D8 has a length of 9 and F8 has a length of 17. So 17, D8 has a length of 9 plus 17 plus 9, 26, and the last one has 21. So 47 is the length, 45 is the length that is available. So at the moment this solution is infeasible, because this bin is using up more than 45 with having a positive value. So even though I have shown a solution with binary values for all the variables, at the moment this solution is not feasible, but it actually does not matter. Only when we optimize we have to check whether we will get a feasible solution. So 4 constraints, one for each bin, are written here. These 4, these all should be less than or equal to 45 times the bin capacity. And since bin 45y1, 45y2 are variables, they are taken to the left hand side. So the right hand sides are 0 and they are less than or equal to variables. Each item will go to exactly one bin. So this is, for example, item 1, it says B7 plus B8 plus B9 plus B10. So if we take the first item, it will go to either this bin or this bin or this bin or this bin. So similarly this will be C7 plus C8. So these set of 8 constraints make sure that each item is going to exactly one bin. So that is written here. Now we go to the solver. I have already mapped it into the solver. So the objective function is this, the number of bins, which is B12. So you realize B12 is the objective function. The variables are all listed here. The variables are all from here. They are from B7 to I 7, 8, 9, 10 to I10. So you see that B7 to I10 and B11 to E11. So the variables are listed here. All the constraints are listed here. The 8 constraints are written here. Now in addition, all the xij's and the yj's have to be binary. So I have to define 36 variables as binary variables, and these 36 binary variables are defined here. To save time, I am just showing you. You can see a bunch of binary variables that are all defined here. So now we are ready to solve this problem. So we go to the solver and we try to solve this problem, and we get this solution. So this is a solution that is obtained by the solver. We realize that only 3 bins are used. You can realize that y1, y2, y3 is equal to 1. So 3 bins are used, and the allocation is this item. The first item is going to the third bin, second item is going to the third bin, third item is going to the third bin, the fourth item is going to the first bin, fifth item is going to the first bin, sixth item is going to the second bin, seventh item is going to the third bin, and the eighth item is going to the second bin. So we are able to accommodate all the 8 items into 3 bins, and now the left hand side also tells us how much the bins are utilized. The first bin is utilized fully, so the left hand side is 0. Second bin is utilized fully, the left hand side is 0. The third bin has minus 15, which means out of the 45 length that is available in the third bin, only 30 has been used and 15 is unused. Now every bin is assigned to, every item is assigned to only 1 bin. So that is how the fourth bin is not used at all. So we have 0 equal to 0 from this. So that is how the solution to the bin packing problem is. So this is an example where we define variables as binary variables. For example, if you go back to the solver, I have defined these variables as binary. Just to illustrate one of them, so all the variables xij's and yj's are binary. So how to add it in the solver? Just go click here. So if you click here, B7 is a xij variable. So if I want to add, I have already done it, so I am just demonstrating it. So I can put add a constraint. Now go to this, B7 is a binary variable. So B7, and click this down, you get binary, you will get binary here, and then you can add. So like this, for the 36 variables you have to add, all the xij's and yj's have to be added as binary variables into the formulation. So this is an example of how we solve a problem that involves a binary integer programming problem. So we defined some of them as binary variables. In this course we did not see the methods in detail as to how to solve binary integer programming, though we introduced the bin packing as an example just to illustrate that not all formulations are linear programming problems with continuous variables. Large number of formulations involve integer variables and binary variables. So just to illustrate that, we had used the bin packing formulation, and for the sake of completion I have demonstrated how to solve the binary 0-1 problem using this solver. Now we move to solving the transportation problem and the assignment problem that we have seen as part of this course. So we go to the transportation problem. So this is the transportation problem that we had solved. So there are 3 supply points and 3 demand points. It is a balanced transportation problem. So this is the transportation problem that we solved. 3 supply points with 40, 25 and 35 with a total supply of 100, and 3 demand of 30, 30 and 40 with demand of 100. Transportation costs are given here as 8, 9, 7, 4, 3, 5, 8, 5, 6 and so on. So let us now try and solve this problem using the spreadsheet. So we go back to this, and I have already created this problem on the spreadsheet. So it is a 3 by 3 transportation problem. So, we have variables x11, x13, x31 to x33, 9 variables, where xij represents the quantity that is transported. The cost of transportation are shown here 8, 9, 7, 4, 3, 5, 8, 5 and 6. These are the transportation costs. So, the objective function tries to minimize the total transportation cost Cij, Xij. So, which I am setting, the Xij variables I am setting here, these 9 variables starting from B5, B6, B7, B5, C5, D5, B6, C6, D6, B7, C7 and D7. These are the 9 variables. The objective function is shown as Cij, Xij, which is put here. For example, F3 into B5. So, F3 is the first value 8, B5 is the quantity that is transported. Like this, I have multiplied the 9 terms, added them and written the objective function, which is like this. Now, the variables are defined here, the values are defined here, the objective function is defined here. Now, this transportation problem has 6 constraints, 3 supply constraints and 3 demand constraints. So, the 3 supply quantities are 40, 25, 35, the demand quantities are 30, 30 and 40. So, whatever that goes out of the first supply point should be less than or equal to 40. So, now I have written what goes out, B5 plus C5 plus D5. B5 plus C5 plus D5 is what goes out of this 40, that should be less than or equal to the right hand side, which is 40. Similarly, the second constraint, which is B6 plus C6 plus D6 goes out of the second supply of 25. So, that should be less than or equal to 25 and so on. So, there are 3 supply constraints, 3 demand constraints. This is what reaches the first destination. So, it is B5 plus B6 plus B7, B5 plus B6 plus B7. The requirement is 30. So, what reaches should be greater than or equal to the requirement. So, there are 6 constraints, 3 supply constraints and 3 demand constraints. Now, we are also aware that this problem is a balanced transportation problem. Therefore, instead of putting less than or equal to inequalities for the supply and greater than or equal to inequalities for the demand, assuming that the minimum demand has to be met, we can substitute all of them by equations. Because the problem is a balanced transportation problem, either we can have all 6 constraints as equations, or we could have the supply constraints being less than or equal to and demand constraints being greater than or equal to. Now, the present solution that is shown is not feasible, because if you see the second supply, 25 is available, but 35 is going out. Similarly, if you see the here the demand is actually exceeding, but in a balanced transportation problem we will meet exactly the demand, because the total supply is equal to the total demand. But as I said, it actually does not matter, it matters only when we are going to solve. So, we will now put the problem into the solver, which I have already done here. So, I am just showing you. Now, the objective function is B9, which is shown here B9. We have already seen the objective function as the sum of these. So, 8 into 5 plus 9 into 0, like that the objective function is written. The 6 constraints are written here. You can see 3 of them having less than or equal to, and the other 3 demand constraints having greater than or equal to. Now, in a transportation problem, the variables xij need not be defined as integer variables, they can stay as continuous variables, and as long as the supplies and demands are integer, they will give integer values. So, we are now solving it as a linear programming problem. We are not solving it using any Vogel's approximation or any such method. So, we are solving it as a linear programming problem. So, we define the variables as continuous variables and use simplex LP to solve this. So, when I solve this, right now for this solution, which is not feasible, as I mentioned, 35 is going out of a supply point which has only 25, and as I said, it does not matter at this stage. So, when we solve this, we realize that we are getting a solution with, so we are once again we solve this. So, we are getting a solution with this, we are getting the solution with cost equal to 565. Now, we also realize that the constraints are all satisfied nicely. 40 is available, 40 goes, 25 is available, 25 goes, 35 is available, 35 goes, 30 is required, 30 is given, 30 is required, 30 is given, 40 is required, 40 is given. Transportation quantities are all shown here with cost equal to 565. Now, if we go back to the transportation problem that we solved, we realize that the optimum solution for this came to 565, which we have here, showing the solution with all the 3 methods which we did by hand. So, Vogel's approximation or penalty cost gave 565. We also said later when we use the stepping stone method, we said no gain and hence optimum. So, the optimum cost is 565 for this transportation problem, which we got from our solution. So, we will look at one more example of the transportation problem, and we will look at a couple of examples in the assignment problem in the next class.